Hello and welcome to this video for Electropages. Today we're here at Avnet Silica and I'm joined by Thomas Hauer Power because we're going to be talking about power, and specifically we're going to be talking about IGBTs versus SiC or silicon carbide. So before we jump into that, just explain to the audience who you are, what you do and what it is that we're going to be covering today.
So I'm the Power FA for Avnet Silica in the EMEA region, so I do also take care of the power team we have. So basically the structure we have for the power electronics is an EMEA-wide approach. So I'm the manager and I do manage the team of Power FAs in the regions, which gives us more, let's say, flexibility and more availability for the customers and their applications.
So this conversation is all about insulated gate bipolar junction transistors and silicon carbide. Now, I think the first question I'd like to ask you is just sort of, for the sake of the audience who may or may not know, just briefly go over the two different technologies and what makes them different.
So IGBTs are devices that are developed in the 80s somewhere, and basically they are 4 PN layers and then kind of different doping, and they act on the input as a MOSFET and the output basically a bipolar, which has the advantage that they can handle a huge current. The disadvantage is they always saturate around the knee voltage that they always have, which is a big of an issue when it comes to not peak load but partial loads or almost no load things, because they always have this knee voltage. And silicon carbides are basically, they build up like transistors but with wide bandgap material that brings up benefits in terms of faster switching speed, lower RDS on for like higher blocking voltage, but you need to have like bipolar gate drive like it is with IGBTs.
So IGBTs have been around, like you say, for about 40 years now. It's because of the 80s. So by me, it's 40 years now that they've been around, and the silicon carbides have been around for 20. But it's really only been around the past 10 years where silicon carbide, it's kind of like exploded. So what is it about silicon carbide that's kind of made it explode over the past 10 years? Why has it suddenly become so popular?
So the big push came since battery electric vehicles been properly introduced to the market. And the thing with battery electric vehicles is they do have peak power, they do have constant power, but they do have average power. And just to give you some numbers, for example, the BMW iX3 has peak power 210 kilowatts, constant power 80 kilowatts, but if you run it, let's say in Central Europe, all over the year with, I don't know, mainly Autobahn usage, it runs at an average 18 kilowatts, 1.8. And so you need to be efficient at 210, at 80, but also at 18. And that's the point. With IGBTs, it's difficult to kind of get this right. It's possible, but not easy. With silicon carbide, it's more easy to have a broader bandwidth of efficiency.
And that comes down to because as you mentioned with the knee voltage, the IGBTs and not IGBTs, they struggle in the lower ends, and so it's kind of like unless you're using them flat out, it's kind of like they tend to struggle. So let's talk a bit about that, because I'm quite curious about this. So what is it about that knee voltage? What is it specifically that kind of makes them struggle at low usage?
You can view the knee voltage at something. So if you, from an abstract point of view, it's from 1 amp to 200 amps. It's like always like 1.5 volts. Right. So it makes it really good at the high end, but let's say 1 amp times 1.5 volts, there you have the losses. And for silicon carbide, they work over RDS on, and this is the losses over the RDS on, so it's like I squared times. And that's really the point. And at lower ends, this is really efficient. What you need to worry about is gate driving and that sort of stuff at the lower end, because that's then your main losses.
Now, just to be clear, these kind of devices, they're rarely going to be used in their linear regions. They'll almost always be used in their saturations, because you use DC switching, you're turning it on hard. But while silicon carbide does provide, the ability to switch, I believe at much higher, is it much higher frequencies it can support?
Yes, higher frequencies, and it's also the result of this is it's fastest switching speed itself. So for
It's the gate response, isn't it, to like when you put a signal in?
Yes, you can, on a simple speaking, yes, it is that you just pull the gate high and it immediately switches on and kind of, it either the output tied to high or to low, whatever. And this is much faster. And if you think of an LLC or dual active bridge, you have 50-50 duty cycle of switch on, switch off. And if the flanks do not limit you in the maximum frequency, you of course try to go high in switching frequency because your transformer gets smaller, and then the whole system gets smaller, and so on and so forth.
So in terms of talking about the switching frequency and the switching speeds, the silicon carbide can go faster than the IGBTs, but I do believe that the issue that by switching faster, they've also got issues with things like EMF and inrush current and things like that. Is that correct?
You do need to rethink your EMI concept. That's right, because maybe your input filters are not filtering at the right frequency anymore. Inrush currents, not so much.
And that's because they can just handle it, essentially. Yeah. It's not an issue. But in terms of gate driving, I do believe that the driving an IGBT is easier than a silicon carbide.
Yes and no. For the IGBTs, you're looking at 15 to 20, roughly 25 kilohertz, and silicon carbide, you're looking at 20 to 90, somewhere there. I mean, you can go further down the frequency route, but most applications stick around 20 to 60 kilohertz. So at that frequency band, challenges change.
Yeah.
And also when it comes to silicon carbide transistors, some of them have lower end gate resistors, some of them have higher gate resistance, and so this it can get a challenge, but it does not have to be automatically a challenge.
But one thing that we discussed in a previous video was about driving silicon carbide transistors, which is that you're actually required to go sort of below the 0 volt gate. And I'm guessing, is that something you have to also do in an IGBT or not? Is that something you also have to do that too?
Yeah, it's both bipolar.
And so why is it that? So then why is it that? It's the impression I get from a lot of engineers is that the type of driving for a silicon carbide is very different, and it's what makes it complicated and difficult to sort of integrate. So why is that? What's going on here then?
I think it's just the higher switching speeds and higher slew rates we're looking at, because that's per se a challenge on gate drivers and on insulated gate drivers, because some of them are just suited for like 10 volts per nanosecond, and sometimes you're looking at 25 or 50 volts per nanosecond. That's a challenge. And also the high side power supply needs to be suited exactly for that application. So there's a bit of there's the need of more investigation to be done on that part of the circuit, but it's not necessarily way more complicated.
And I think, if I understand this correctly, that faster switching speed, that's where you can improve your efficiency because essentially you're spending less time in the linear region. But when you do that, I believe that you get some. I think you might get issues in terms of the gate driving itself and how that pattern looks. Because unlike a typical transistor where you might just sort of go on off, don't you have to have sort of like pre-charged set zones and then you come up and then it's.
It does not have like the milliplateau. It doesn't have the milliplateau like a standard transistor. It's more a knee thing.
It goes up like this.
And then stays at constant, but it's not like the milliplateau where it then switches on. It's
and
just
that's the gate driving part, isn't it? So
yep.
So you kind of like ramp the voltage up a bit. You can then go up, and then you maybe.
Normally, you just switch it on hard as fast as you can, and then you're good. There are new developments where when you're switching off in a kind of emergency state, the gate driver has an extra pin to just bring the silicon carbide transistor in a safe state before it then hard switches it off. That's new features that are coming with some gate drivers. But normally you just switch it hard on, switch it hard off, and then you have like either split gate drives where you can decide on the switch on timing or the switch off timing, or you have active Miller clamp.
So let's talk a bit about that safety aspect. So what challenges can happen in that situation if you shut it off too quickly?
Too much energy dissipation in the silicon carbide itself. And the thing is, silicon carbide has a lot better thermal conductivity.
Yeah.
And so this gives the advantage to bring the heat out really quickly. And if you're talking about 400, 500 amps that are switched, that's not like 1 amp DC-DC.
No, there's a
12
huge
voltage.
amount of current.
Sometimes it's the case to just draw back the current a little bit to actually use the linear region of the silicon carbide MOSFET, bring them to a safe state, and then really switch them off hard.
So it's a case of just preparing the device
Yep,
to accept that large current before you get. But what you're saying is that if you switch it off too fast, you get a massive dissipation of energy in that die itself, and then that's going to damage the part.
Yeah.
And is that because the dies have a higher power density and therefore they're made smaller, therefore they've got to try and handle this huge amount of power in such a small space?
It is indeed a kind of challenge in the design, because what semiconductors companies are trying to do is kind of get the most out of their wafers.
Yes.
So the nature of thinking is making the die smaller and smaller and smaller. And but if you make the die smaller with just thinking of the same RDS on, the losses within switching stay the same. So you have the challenge, you have less silicon carbide that cope with the same amount of losses in switching, and just take this kind of fact further. It's like, okay, if you have a smaller volume and then switch off, it's more of a problem for the die.
So that's actually quite interesting. So by making the die smaller, you can fit more on a wafer, which helps to make them more economical, which also I would suspect would reduce the size of the end device, which means that you're getting more higher power density, so the device becomes smaller. But like you say, as a result, there's also more power per square, I don't know, inch, millimeter, whatever it is. And as a result, if you have that high inrush current or that high energy dumping, it's just going to stress the die, essentially stress everything out and cause serious issues. So, in terms of maximum, sort of, let's say like, I don't know, power per, or like watts per square millimeter of coping, if that makes sense. How do silicon carbide devices compare to IGBTs?
IGBTs are way more ruggedized than the silicon carbide, but they have to be because of the slower switching. So, but this IGBT die will always be much, much larger than the silicon carbide die, and that's the point. I mean, silicon wafers are huge, so that's the advantage. You still can produce them in a very economical way. But think of IGBTs being really more ruggedized and being able to take more overload than the silicon carbide can.
But if we were to say, like, let's say for a typical, let's say for one every 1 square millimeter, IGBTs can handle something like 100 watts. What would it be for a silicon carbide, do you think? It would be a bit of a hard number to come up with.
That will be a wrong educated guess from my side.
Fair enough. Because I know. So let's talk. Let's look at it from this point of view then. Let's say So we know that silicon carbide is about 1200 volts. Is what its band gap. What's the band gap, would you say, of an typical IGBT? 600, is it?
No. So you mean that the blocking voltage?
Yeah.
For IGBTs, it goes from 600 volts to 3 So with our suppliers, I think we're having 1.2 kilovolts is the maximum.
Okay, so they can go really high then.
Yes.
And what about the silicon carbides then? Are they stuck at about 1200 or is it?
No. They're going up to 2.2 kV.
Oh, okay.
And some of them even go high already, and they're aiming for, let's say, higher voltages. And IGBTs go up to, I think, 6.5 kV, but not with the, let's say, industrial automotive landscape we're supporting. That's more railway applications and these kind of things.
And why is it that they don't support automotive and industrial?
IGBTs?
Yes, they do. In that case where you've got the 6 kilovolt ones?
Because automotive does not use voltages above 1500 volts, because there's a different insulation standard that takes place that makes things way more complicated. So they try to stay below the 1500. And for industrial, it does not make that much sense, to be fair, because you normally have link voltages 800 volts ish.
So I just remembered the sorry. So I think the 1200 volts for the silicon carbide. That's the dielectric breakdown, isn't it? That's the point where. And so what would it be for IGBTs at that?
You mean the breakdown voltage?
I think so. Yeah, I think so. That's what I meant. Yeah. Because it's silicon, isn't it? It's just a silicon technology.
Yeah, it's silicon technology.
So it'll be whatever silicon is, but I'm not sure that is. That 600 volts, is it, or something?
I need to. I'm terrible at remembering numbers.
Oh, it's too many numbers because I know like the what is it? The it's like it's conductivity. I think it's about 3 times as high, and I think it's what's its the
electron mobility is.
That's
higher.
what I'm trying to think of. Yeah, it's much higher. It's a much higher electron mobility, isn't it? But GaN's even higher, but it's got a problem with breakdown. It's got a lower breakdown than silicon carbide, but it's much more conductive.
Yeah, and you need to think of. I mean, silicon carbide devices are purely made of silicon carbide.
That's right, yeah.
And GaN devices are not pure GaN devices.
They'll have other things attached to them as well.
GaN devices are made on silicon. So it's basically a silicon base layer, then there is a buffer layer, what you call it, and then there's the GaN structure grown on it.
And I'm guessing that they do that. So, so they do that because it allows. Do they integrate electronics into the silicon wafer itself to control the GaN, or is it a case of just having a medium for it to sit on, sort of thing?
The silicon layer, the silicon layer itself is just a medium to sit on.
Oh, okay.
All the integrated GaN devices you see in the market are, so at least with our suppliers, are fully GaN.
And so let's bring the conversation back to silicon carbide because GaN's for another story. But in terms of IGBTs with the device itself, I'm guessing it's kind of a more. Would you say it's a more complicated structure compared to GaN, or would you compared to silicon carbide? Sorry, because I take it silicon carbide device is just silicon carbide, but an IGBT kind of has to have extra parts around it to make it work.
From a design point of view, you see the same parts really. So because the requirement is bipolar gate driver, that sorts of stuff. That makes it kind of the same thing. It depends when you're doing like a traditional boost stage. When you swap IGBTs for silicon carbide, you might rethink the snubbers you have on the high side diode and stuff. That's a bit of a mixture. And when you swap silicon carbide in for an IGBT, you might rethink your booster diode itself, because normally with IGBTs it's a normal silicon diode, then you need to use either a silicon carbide diode or an ultra-fast rectifier to be able to handle the faster switching.
So in a previous video we talked about silicon carbide as being having an insulated gate, which means it's basically like an NMOS essentially. But even though it's an insulated gate, which in theory is not supposed to have much, like it's supposed to have zero input current, because of the fact that it has a gate charge and that gate charge happens over such a tiny period of time, you can have, I think you were saying something like as much as 6 amps going into one of these devices during the switch?
Exactly when you switch on or switch off. Because you need to consider you have, as an input, the device reacts like a capacitor and some resistance. And just go through this kind of low pass, no, not low pass, just go to this filter, RC filter, and think of it as it is. And when you switch on, you have 15 volts for the modern devices, and the capacitor is 0 volts.
So compared to silicon carbide, I think insulated gates you're saying could be around sort of like 1 amps or so peak current typically.
Yes, you also will see 350, 500 milliamp gate drivers around.
And so they're quite low compared to silicon carbide, and that's where that complexity comes in, because when you're multiplying the inrush current, or that inrush current by about 6 times, you've got to make sure that your resistances to that path is completely minimized. You've got to make sure that the gate driver can do it that quickly. It can survive that sort of current, that sort of inrush current. And that's when we also talked about the idea of microcontrollers. So you said that some microcontrollers out there can actually drive IGBTs directly.
No, MOSFETs, the logic level MOSFETs.
Oh, okay. I thought you said that some STM devices had.
You mean the ST spins? But they are microcontrollers with dedicated gate drivers in.
But they've still been able to integrate it, so that means that you can have an IGBT controlled by one of these microcontrollers. But But in terms of silicon carbide, because of that massive difference, it's just not something that's going to be possible in the short term.
Possible maybe. I would not rule that one out, but it's always a thing of practicability because it depends. Silicon carbide is aiming at the bigger power, so we're talking 3 kilowatt onwards. And when you're thinking of a motor drive that's driving 50 kilowatts-ish, we're talking a PCB about this size.
Yeah.
And power switches maybe here, microcontroller maybe here, and then you have the peak gate driving currents over half of the PCB. That's not really what you want. What you want is at a physical bigger size, being able to position the gate drivers right next to the gate, which is not possible then, which makes no sense. I mean, technically, I think it's possible, no issue there, but from a design point of view, it doesn't make that much sense, I think. And for IGBTs, it does make sense because there's the small power modules with like this form factor with a B6 bridge in there. So there it makes sense. You can place the microcontroller quite closely and do all this stuff.
And so if an engineer is going to choose between an IGBT and a silicon carbide, what do you think is going to be the points they need to consider? Why is it they'd go for one over the other?
You need to look at your whole topology. Is it a PCB that's going to be very close to the motor? It's worth considering silicon carbide. If there's a significant distance, stick with IGBTs because the wire introduces wire-to-wire capacitance, and when you switch fast and you switch capacitance fast, it's basically a short circuit there, and that's what damages then the device.
Oh, that's interesting. So it's not just a case of, if I've got an EV and I'm going to power it, use silicon carbide. It's a case of, well, hang on, where's the actual sort of power driver for that thing in the first place? That's really interesting. So I know that in terms of with things like power cables, I know if you use a twisted pair, you can reduce the inductive nature of those wires, but that's not going to change the capacitive nature of that wire at all.
No. What they do for industrial robots, they can use specially like insulated and shielded wires, and some of them do, but they come with an extra price. So the motor inverter must have a significant improvement in efficiency that this wire installment has its kind of sense. Otherwise, just stick with IGBTs because you're more safe. And the thing is, with automotive applications, the inverter always sits like on the motor.
Right.
When you think of big robot installations in factories, there's like the robot over there and the inverter is over there. And you have like 50, 100 meters of wiring, and that's a proper nightmare for fast switching.
And so again, in that case, because of the fact that in the case of the industrial application, space is essentially free, and so it doesn't matter if something is twice as big in terms of power handling and control. So again, IGBTs are probably going to be okay in that application. Long, big cables, it's better to use that. And I think it would be fair to say that, especially when we've been at a lot of these trade shows, when they talk about silicon carbide as being the next big technology, that's something I've never heard an engineer say before about, or going into the actual important details about like with cable. Like for example, if you've got a long cable, the capacitive nature of that cable is going to cause problems. Do you think that engineers currently are struggling to sort of try and understand the technology correctly?
It's not struggling. It's, I think, lack of knowledge at some point. And it's also kind of down to the education they have, because silicon carbide is not kind of in the education plan at universities at the moment, because it's kind of
such a new technology.
Yeah, and it will change in future, of course. But at the moment, there's a lot of let's say, insecurity, because lots of, let's say, one pages are out there like everything will be SiC and SiC is the future. That no, IGBTs will stay there, and they will have their play in the future as well.
Yeah.
But silicon carbide is another thing you can use that might improve your design, but not necessarily. You need to look at this, and when we look at recent market studies, IGBT has a prospective growth rate of like 4-6%, I think, and silicon carbide is still at like 25-30-ish%. And of course, this is something that's more exciting to talk about.
That's always going to happen with any new technology. But that doesn't. But what you're essentially saying is that doesn't mean that IGBT is going anywhere. In fact, it's still growing, and that's because as power levels go high, as we increase power levels, battery level, voltages, all these different things. Like you say, if you've got an application where a silicon carbide device is not going to survive, IGBT will step up and it will still be used. Now that doesn't also mean that there still haven't been advances in IGBTs. There's still
investments. There are still investments. For example, onsemi just released the newest field stop 7 technology, which is a really great enhancement of the old technology, and it proves the value for suppliers, and that's the point. So it's important to stress the fact that they don't go away; they will stick there.
So even though silicon carbide's had this massive growth in the market, like 25% year on year or so, the IGBT sort of like industry still is still seeing growth. So it's a technology that's still relevant today and will continue to be relevant because people are still investing in it.
Yes, companies keep investing, and that's for a good reason, because there are some applications you can't just simply not address with silicon carbide, and most OEMs for cars at the moment, the motor in the back, silicon carbide, motor in the front, IGBT, because it's a booster motor.
Really? Different technologies in the same car?
Yes.
Oh, blimey. So
and you don't need to have it permanently on. You just need it when you're accelerating on the Autobahn or whatever. And it does not need to be super efficient. So you can kind of go for a technology with a smaller price tag. And that absolutely makes sense.
And that's your sport mode, so where you accept you're going to lose power, but you're going to get that speed and acceleration. But when you're doing eco mode, you'll use the back wheels closer to the so the driver and the power source are all close to the wheel, so you don't have those long cables. So silicon carbide will do a much better job.
Yes.
Now, one thing I'd love to point out about this episode, and I think this really goes to show the strengths of an engineer using Avnet Silica, is the fact that in this sort of like 30, 40 minutes we've been sat here talking about the technology, you know, the kind of questions the quite engineering questions sort of thing. I've been able to get answers for stuff that tends to be quite hard to find online. And so I think I'd like to sort of bring attention to the fact that you guys at Avnet Silica, you can help engineers who have these questions, have these same problems, who might come to you and say, which one should I use, IGBT or should I use silicon carbide? And so is that something that you guys can definitely help with engineers out there?
Yes. And that's, like, let's say, a big part of our job to advise on which technology they can use and what makes sense, what does not make sense. And that's why we encourage customers and engineers to just come to us and talk to us, because we can, like, help you to go over step, like, fall over traps and whatever in the technology, and just eliminate extra rounds in engineering because there was something they were not looking at. And always Googling for information, it's just like...
It's tricky.
It's tricky, and it's always just like half the information you get out of it is like based on the question you type in, and it barely works out correctly.
And something I tend to find as well now is especially with Google, not just Google, but I've seen it with other search engines where you start to see that they're starting to spit out AI answers. And so when you have cutting edge technologies like GaN and silicon carbide, you know, personally, I'm not too comfortable with something giving me some advice that may or may not be right. But if you go to you guys directly, you deal with the technology on a daily basis. So in terms of the offerings and the solutions that you have in that field, I'm guessing that would include everything, almost every aspect of silicon in power, everything from controlling it to actually delivering it and conditioning it.
Yes, there's from, let's say, the power switching device itself. Maybe it's silicon carbide, GaN. Silicon can be a standard MOSFET or an IGBT. And then the gate driver, the supply for the gate drive, then the microcontroller. There's kind of my colleagues taking care of that one, and then signal conditioning and whatsoever. So we have for each and every kind of part of the schematic, we have the experts. You can ask and draw in and then ask questions. And please ask the difficult questions, because that's where we are there for.
And like you say, if you ask the right questions, if you ask the difficult ones at the very beginning of your project, that's going to save you time and money in the future. And I would probably say it would get you to the market quicker as well, which in an industry like power, it's probably I can imagine it's very competitive.
It is competitive, but most of the, let's say, projects go over a year or two.
And that's simply due to the safety aspects, the high power aspects, the need to do thorough testing, all these kind of aspects.
Testing. I mean, when you test the device, you do temperature test, you do efficiency test, you do MC testing, then 1,000 hours test. I mean, it's 1,000 hours.
It's 1,000 hours. Yeah. It's a lot of
and
testing.
And if something goes wrong there, you repeat 1,000 hours. So that's the point.
I can sympathise because I've tested stuff for the aviation industry before, and if it goes wrong, it's a huge amount of money, it's a huge amount of rework, and it's something you don't want to do a second time. So I totally understand that a 1,000-hour test a second time is not going to be fun. So sort of like as we're getting to the end of this video, I think a question I'd love to ask you, especially when it comes to silicon carbide and sort of like IGBTs, what's the most interesting project that you've worked on with a customer from Avnet Silica's point of view? What was it? Assuming you can tell us, because I know sometimes you can't.
Actually, would love to, but basically it's about custom power modules. Where we're diving into module layout, so just pin out and how to place, let's say, the dies internally and how to get the wiring done and stuff like this. This is really something you do not see quite often, and it's always interesting because normally you see the finished product and try to put it into a PCB, and they was like, okay, I was involved in actually getting the finished product done in the first place.
And so in that case, it was. So what you tend to find interesting are the power modules themselves.
It's the power modules themselves, and you just sinter dies on it, and then you kind of wire bond and sort of stuff, and that's nothing you see like every week.
Because it's just so different. It's not.
Yeah.
That's really, really interesting. Okay. So my last question to you, for the audience who are watching this video, if they want to get involved with silicon devices or silicon carbide through Avnet Silica, what would you recommend that they do?
Contact us over the website, LinkedIn, whatever find most convenient. Maybe you know already a salesperson that's working for Avnet Silica, then call this person. They will find us.
And if you really need a power solution, Thomas Our Power is your solution. Fantastic. Thank you ever so much.
Yeah, thank you.
Thank you.